So let's say we have, this is, input is y, the output is, let's say, x, k, b. So as we know, the differential equation of this system is mx plus bx dot plus kx equals, I don't know, something is wrong with this pen. dy dot plus ky, then the transfer function of this system, which is the output x of s by the input, which is y of s here. You take the Laplace transform, ignore the initial conditions, you get this will be the transfer function, for example. So it transforms the output to the input in a way. You can think about it as y of s is a signal that comes into the system input, multiplies g of s, okay, x of s is in parentheses. Or in general, this is the output here. In general, we say this u, the notation we use is u is the input, okay? And g is the transfer function, and y is the output. Usually this is the notation we use. And y of s equals g of s times u of s. It multiplies, the output multiplies the input, and we get the transfer function. The transfer function gives us the output. So this is something we have done before. Today we will be looking at certain properties of transfer functions, which are poles, zeros, and the so-called DC gain. Okay? So the transfer function of a system, as we know, in general, is a ratio of two polynomials, a numerator polynomial and a denominator polynomial. And let's say that this is of order m with coefficients b1, b2, etc., plus, let's say, bm. And then you have s to the n plus a1, s n minus 1 plus an. So it is a nth order polynomial divided by an nth order polynomial. This is the numerator polynomial, the b terms, and a terms polynomial with the a terms is the denominator polynomial. Now we can, these are polynomials, and these polynomials have roots, of course, okay? So we can put them like here, if you like. S minus dm. So we have m roots in the numerator and n roots in the denominator, and there has to be a actually some kind of a constant parameter in front of that, but it doesn't matter here. Let's call it k bar, which is not very important for us, but this is necessary as we will be seeing. Now, the roots of the numerator z1 to zm they are the roots of n of s. We call them the zeros of the system. Okay, and p1 to pm, which are the roots of the denominator polynomial, are called the poles of the system. Okay, why do we do that? Because at the value of this, the transfer function at the value of the zi, if you substitute a value here of the z, any root, this will be a 0. So the transfer function will exactly be equal to 0. And at the value of the pole, g of pi, as you know, is kind of infinity. So at the value of the pole, if s is equal to pi, the transfer function will be equal to infinity. It doesn't have a physical meaning. That's why we call them zeros and poles, actually.
Hocam, I'm so sorry to interrupt you. I think I'm lost in the equations and the concept. May you explain briefly from the poles and zeros?
Well, you have polynomials and roots, right?
So those are like constant things for poles, zeros, and DC gain.
Yes, kind of. For example, let's take this example. Let's say the above. Let me write above example. Let's say that m is 1, b is 10, k is, let's say, 100. Okay, I think I have done this before. So the g of s is 10s plus 100, and then it is s squared plus 10s plus 100, right? G of s. So the zero of this system is, 10s plus 100 equals 0 gives z1 is equal to minus 10, right? There is a 0 at -10 of this system. And then the s squared plus 10s plus 100 equals 0 gives you the poles of this system. The value of s at which this satisfies this equation is P12. They are complex poles, -5 plus minus 10 root 3 over 2 j. They are complex, right? So this is a 0. These are the poles.
Okay, hocam. Thank you so much.
So we can write our g of s as follows, if you like. G of s equals in 10 times, let's say s minus, we should say s plus 10 divided by we can say the following: f plus 5 plus root 3 over 2 squared, as you might remember. Okay, the complex poles can be written like this. Okay. So poles and zeros are two definitions, two concepts which are important. There is something also important, which is called the gain of the system. Well, I shouldn't say gain, I should call it something else. Let's call it steady state gain. Which is also called the DC gain. Okay? This is again another important concept. And for this, we need something from the Laplace transforms. Let's remember the following. I think I have talked about this. The final value theorem. We can shorten it with FVT, which says that if you have a function y of t, and if you want to find its value at infinity, that is where it goes at the value of infinity, can be found from its Laplace transform, as its Laplace transform goes to 0. Okay, this is a very important theorem. We will be using this over and over again, actually, later on in this course. So let's put it in a box like this. It looks trivial or it looks unimportant, but we will see it is quite important in terms of finding the system properties. Well, now the gain of the system is basically the value, the steady state gain. Steady state, what we mean by steady state, actually, let's define this. The state at which things settle down, all, let's say, time derivative terms go to 0, let's say, okay? So if you think about it, for example, let me just take this example. Again, a mass spring damper system, MKB. This time, let's have a force acting on it, and this is X. So this system has a equation of motion mx double dot plus bx dot plus kx equals f of t, as you know. Okay. Of t. Now, if you have this system, and if you suddenly put a force on this system, what happens? A force that is constant. Let's say f of t equals some f0. Okay. X is going to go to well, assuming that the system is stable and so on. Eventually, this system will make such a motion. This is x of t. X is initially at 0 value, but then it will start oscillating. It will oscillate and come to a standstill. At what value will it come to a standstill? At what value will all the derivatives go to 0? This is the region where you have the so-called steady state. All the derivatives have gone to 0, and this region is called the so-called transient region. Now, as you see, in the steady state value, steady state, you have the time derivative. The first and second time derivatives are 0. So our equation is like x at times x at steady state will be equal to f0, right? So we have settled down at a steady state value here. And as you see, x steady state will be f0 over k, right? So the value, steady state value of this system is the force amplitude divided by the spring constant, as you can see. That is more or less clear. But what is the gain of this system? What is the steady state gain? When we say the steady state gain, we mean the following. Output, let's say, over input at steady state is equal to the steady state gain. For example, for this system, output is f0 over k divided by the input, which is f0. So the gain of this system is strangely 1 over k. So the steady state gain, for example, for this system is 1 over the spring constant. Okay. Well, it is called a DC gain, as we know, because it's electrical engineering terminology. For example, if you have something like an amplifier, let's say, if you have an input of 0.1 volts, and if your output is 10 volts, let's say, of course, there has to be an external input to the amplifier. If your input is 0.1 volt, output is 10 volt, the gain, the DC gain of this DC gain, which is equal to the steady state gain, okay, steady state gain, is output, which is 100 volts divided by, sorry, 10 volts, 10 volts divided by 0.1 volts is 100. Okay, this is the so-called the gain value, the steady state gain value, or the DC gain value of this system. Okay, so the steady state gain concept is kind of clear, I suppose. It is the output over the input at the time when the things have settled down. Nothing changes anymore. Okay. How do we find it from the transfer function? The transfer function. Well, we know that y is g times u. Okay. Let's say that we apply unit step input. Let's say that we apply a unit step input on our system, which means that u of s, as we know, is 1 over s, right? So for a unit step, we want to find the value of the output. So the output in time is going to be something like this. If your system is stable, eventually the output y over the time, y of t, will come to the steady state value of y. Okay? So we want to find the gain, which is the steady state value of y divided by the steady state value of u. And we can say that this is, we don't say that. We can note that the steady state value of y is the y at time equals infinity, okay? When things have settled down. By the way, we will be using the final value theorem, but let's go back to the final value theorem. A very important thing is that if you want to use the final value theorem, you know, the y of t must be finite, which means that the system generating y of t must be stable. Okay. If you don't have that, you cannot use the final value theorem. So, what do we do? Okay. So y of s equals g of s times u of s, which is g of s times 1 over s. Okay. So it is g of s over s, if you like. So we want to find the y at infinity using the final value theorem, which is the limit as t goes to infinity of y of t. Assuming that this limit exists, this is by the final value theorem is equal to limit as s goes to 0, s times y of s, which is limit s goes to 0 of s times g of s over s. These s's cancel, so this is kind of g of 0. Okay. So y at infinity is g of 0, but this is also the steady state gain k is equal to y at infinity divided by, well, u at infinity if you like, but this is y at infinity divided by 1 because we have selected it to be 1, but this is equal to g of 0, okay? Provided that g of 0 is finite, of course. So the DC gain or the steady state gain, k equals g of 0, is a very simple formula for determining the system's steady state gain, which is a very important property of a system. Let's say that you have g of s equals, let's say, 5s plus 25. Let's say, I'm just making this up, s cubed plus 5s squared plus 10s plus, let's say, 100. I just made up all the numbers. Now, the steady state gain of this system is simply g of 0. You just substitute s equals 0 here. This will be 25 over 100. So the k in this system is 1 over 4 or 0.25. Okay? This is an example. So the concept is quite simple. For example, if you have a, let's say, a tank system like here. By the way, okay, let me just, you have a tank system. A water tank.
Hocam,
yes.
This K that we found, this is only applicable for when the input is a step input, right?
No, it's a property of the system. It's not applicable to, it's a property, it is a general, it is when, you know, things settle down, eventually, for any kind of input, this is true, okay? Well, it is only true, of course, when things are settled down. It is a value, it is a gain at which the derivative, time derivatives are 0. So you have to have some kind of an input, which is something like a step, you might say. Yes, that's kind of true.
Because like, if the input wasn't a step input, like the s's wouldn't cancel, right? Because we multiplied with s, the transfer function.
Yeah. Well, we chose it to be the step input because we know that with a stable system, with a step input, the system response will settle down. That's why I chose a step input. Okay?
Okay, hocam. Thank you.
Okay. For this system, we have, let's say that the Q in is the input and the H is the output. So the transfer function of this system is H of S divided by Q in of S. Okay. We have done this before, so I will just write it down here. It is R over ARS plus 1. This is the transfer function of this system. Okay. And as you see, for this system, the DC gain or the steady state gain K is equal to G of 0, which is equal to R. Okay. So the gain, when you have a unit value increase in the Q in, the height increase is proportional to R. But on the other hand, if you define another transfer function for the same system, G of S equals, let's say Q out of S divided by Q in of S. In this case, this will be a different transfer function. The denominator will be the same, but the numerator is different. Instead of R, we have Q1. Here, the K, let's call it G, I don't know, G bar. In this case, K bar is going to be G bar of 0, which is 1. Which makes sense because when we consider the flows, the output flow should be equal to the input flow when the height does not increase. At steady state, the output and input flows to the system should be the same, right? As you can guess. So, as you see, if you define your transfer function with different variables, your steady state gain also might change, by the way, as you can see. Okay, any questions up to here? So we have defined poles, zeros, and the steady state gain of a system. Now I will introduce another concept which is quite important in the analysis of systems, and this is then impulse input. What is an impulse input? Well, let's say that you have a system, very simple, let's say mass spring system like this one. Okay. You put an input to this system, force, F of t. But this force is as follows. You know, if you put a constant input, that would be a step. But you put a pulse, that is, you put an input, which is very kind of high, a large input. This is F of t. And that large input lasts for a short time. This distance is, this is time, t. And this is the, let's say, the amplitude f0. Okay. So this is the input to the system. You put a force, like hit it with a high amount of force for a very short time and observe the response of the system. Okay. Now the idea is the following. We put an input that is, this is a pulse, by the way, this is a pulse input. But we want something more than that because it is quite useful. What you do is, let's say that the area here is 1, let's say that because, which is f0 times t, so that when f0 is high, t is small, and so on, we let this t go to 0, and eventually we get some input like this. This is not a real input, this is an ideal input, okay? So when time equals 0, this input is 0 until at all times actually. But when time equals 0, it goes to infinity. So we call this delta of t, which is the impulse function. Its properties are that, first of all, delta of t is 0 when t is not 0. Okay, it is only non-zero at t equals 0. Okay, and another property is that its integral over the time is 1. Okay, that is, the area underneath this thing is 1. It looks it looks strange. It is not very realistic. It is not something you can achieve, but you can only approximate. And this function has a certain name because of this physicist Dirac delta function. And it's not a real function, but anyway. But as a test input, this input is an important input for our system. As I have said, we can never achieve this kind of an input, but we can approximate it. But it is a useful tool for the analysis. This is important because of the following. Important, let's say, since the Laplace transform of this delta function is simply 1. Okay? If you take the Laplace transform of this function, you get a 1, which is very useful because when you apply an impulse, delta of t, we have y of s equals g of s times u of s. So you have u of t equals delta of t. And since this is 1, this is simply g of s. The output is simply the transfer function itself. Okay. The transfer function g of s, as we know, is made up of s minus z1, s minus z2, a general transfer function s minus zm, divided by s minus p1, s minus p2, minus pm, and pn. Now we can express this with partial fractions like c1 over s minus p1 plus c2 over s minus p2 like this. Okay. Now, let's say that we apply an impulse input. So y of s equals g of s, which is this thing above. So y of t is the inverse Laplace transform of g of s, which is the inverse transform of this, which is the inverse transform of all these terms, which I will, okay, let me write it, C1 over S minus P1 plus. Okay. What are these? These transforms are known actually. Y of t is simply C1 e to the P1t plus C2 e to the P2t plus Cn okay. Now this e to the pt term is interesting. What is this e to the pt? It's an exponential. It is an exponential growth or an exponential decay, right? First of all, it depends on the value of p. If p is greater than 0, this is what you get. This is time. This is an exponential. This is not e, but p. P is greater than 0. Right? So you have an exponential growth here. And this is something we don't like in control systems, because this means that the system is unstable. With an impulse input, your response grows up. We would like to have response like this one, usually. And this is possible if p is less than 0, which is exponential decay. Okay. And if you have p equals 0, you have the following, neither growth nor decay. But you should have this is something we require. This is something we want from your system, because remember that these P1, P2 to Pn. These are the poles of the system, okay? And these poles determine the character of the response. So think about it. What happens if one of the poles has an exponential growth? All the others decay, but one of them grows. The system response is going to grow up, okay? It is going to be unstable. So very shortly, we can say the following here. So we can say that the poles Pi determine the stability of a system. Well, we have assumed that the poles are real, but this is not necessary. For stability, we need the real part of Pi poles should be less than 0 for all poles. Okay? Because if one of the poles is unstable, the response is going to grow up, so it will be unstable. So let's say even if one pole is greater than 0, the response is unstable. And unstable is something we don't want. For example, let me write this and then I will finish and take a break. Let's say that this is S plus 1. The zeros don't influence stability. They influence the response. Okay. So here you have one of the poles, P2 is -2. This is okay. But here, P1 is 1. And this is not okay. This means that the system, the pole is positive, so it is unstable. This is an unstable pole. Okay. The poles can be complex. For example,
Hocam, can I ask a question?
yes.
Hocam, what if S is equal to 0? Does it affect the stableness?
Well, it is, if S is equal to 0, it is neither stable nor unstable. It is just, it's something in between.
So
Okay.
if we have a system that one of our pole is 0 and the rest of them is minus, so what will happen?
Well, that system stability depends on your definition. If you want a bounded output, the system is not stable, okay? You can call it unstable because the output is not going to be bounded if you have a step input to that system. But on the other hand, if you want for, let's say, different kinds of inputs, it might remain stable, but that's a, you know, kind of a difficult topic for now. So let's skip this for the time being. Let's say that it is neither stable nor unstable. Okay. That is in the limit, let's say. You might have poles that are, let's say, something like S squared plus S plus 1, which gives you, the poles would be minus 0.5 plus minus j root 3 over 2. And as you see here, since this negative part is negative, sorry, the real part is negative, it means that this is a stable pole, okay? The real part of the pole should be less than 0 for all I. Okay, let's take a break here. We are very late, by the way, so. So we found out the condition for stability. We will look at stability more in detail later on. This is just a very basic introduction. Now, as you see, we are moving from concrete, real physical systems to things that are abstract. That is, things like poles, zero stability, impulse response, etc., are quite abstract concepts. But eventually, from this abstractness, we are going to be designing systems, and those systems are going to work perfectly. That is, we are going to go back to concrete systems again. So although this looks like a little bit strange to you in the beginning, as you will see, we will be doing things with these concepts, and these concepts are going to help us design good engineering systems. As we know, we have transfer functions, and the transfer functions we have are not just remain by themselves, but we connect them. That is, we connect physical systems, such as we connect a DC motor to a gear system, and that gear system is connected to a valve, and that valve opens and closes a flow to a tank, etc. Different kinds of systems are physically connected to each other. So those connections, in order to represent those connections, we have the block diagrams, which to represent those systems connected to each other. I have talked about this before, but let me just very briefly talk about it. The very basic block is, as you know, is the transfer function block, u and y, u being the input, y being the output. Then we have these things, these blocks connected in series like this. Let's say u of s, let's say this is x of s, this is y of s, this is g1 of s, this is g2 of s. This is, as you know, is this g2, g1, u and y. We have another thing that is branching. So if you have u coming in, this is u supposedly, and if you branch from here to 2, you will have u comes in, it branches, well, it doesn't divide into 2, but eventually both sides get the same u, okay? So it is the signal that is flowing here, not a physical thing. Let's call it G1, let's call this G2, let's call this Y1, let's call this, sorry, Y1, this is Y2. And another thing is this summation point, okay? We sum up signals, and again, this thing. Y is equal to y1 plus y2, which is y1 is g1u plus g1u plus g2u. So y is equal to g1 plus g2. Okay. So the block diagram algebra represents systems like this. And one more thing is the feedback loop. I think I have done this, but let's do it again. Let's say that you have, this is something we will do over and over again. Again, there is something wrong. R of S is the reference signal, let's say. Let's say that we have some C here. This is H. So C is the controller. G1 is G, well, I shouldn't say G1, it is just G. And H is the feedback transfer function, which is we might call the sensor. We will, as you will see, I don't know why this doesn't work. There is something. I guess this pen there is something wrong with it. Excuse me for a moment. It is, I have to, so, let's call this E. Let's call this signal E. This one, let's call it M. And let's call this YM, the measured value of Y. This is R of S. This
Hocam,
is
you
Hocam.
didn't share the screen.
recording. Huh? Is that
Hocam,
okay?
you didn't share
Sharing
the
the screen.
I didn't share the screen, I'm sorry. Okay. This is okay now, right?
No hocam.
No? Ah,
No.
okay, now it is okay. It should
It's okay now.
Yeah. Now I can say.
All right. So I have introduced the signals. This is the error signal. This is the so-called manipulated variable. This is the output. And this is the measured output. We want to find out the transfer function between the input R and the output Y. Let's say this is the output. This is the input to the system. So we will go step by step. As you see, Y is equal to G times M. Okay? But M is equal to C times E. So G times M is C times E. C times E. Why does it do this? I have no idea. C times E. But then E is, as you know, is R minus YM. So you can write Y is equal to GC times E. E is R minus YM. YM is what? H times Y, right? But we have Y on both sides. So we can write this as GCR minus GCHY. We can carry the Y to other side and we get Y plus GCH HY equals GCR. So you can put it into Y parentheses and get the following: Y 1 plus GCH equals GCR. So you can say that Y over R, which is the closed loop transfer function of this system, by the way, is as you see. This is the closed loop transfer function. In the closed loop system, the system is reduced to the following. This system can be, if you want it to look at it from outside, this is R is the input. Let's call the closed loop transfer function T, and this is Y. So in a way, this thing is T is equal to Y over R, we can say. Okay. As we have seen, this is the closed loop system. The closed loop system has different poles and zeros than the so let me write this. G is the open loop system. T is the closed loop system. And you see they are different. The poles and zeros and the steady state gains of these systems are different. As a matter of fact, the closed loop system changes the dynamic response of the original system and makes it, makes it a different kind of system. Let me just give you an example here. Let's say that we have let's say that we have the following. I just made up these values. This is the feedback. Plus minus. By the way, I didn't tell you, there is a minus here, as you can see. This is a minus, okay? This basically means negative feedback. Okay, because of this minus, you have this term here. This is negative feedback. Negative feedback, you know, the name is negative, but negative feedback is something good. It usually stabilizes the system. So don't fall for positive feedback is something not so good. It usually destabilizes the system, okay? That minus sign indicates negative feedback. Negative feedback has stabilizing effect usually. It moves the poles to a more stable region most of the time. So for this system, let's say we want to find the T, which is Y over R. And this will, if you call this G, and if you call this H, there is no C. C is equal to 1 here, okay? The C term we had in this example is 1. So it is simply G over 1 plus GH, which we can write as follows. Let me write it here. Then we will have space. 3 over S squared plus S plus 2, 1 plus G, 3 over S squared plus S plus 2 times 2 over s plus 3. So we equate the numerators and denominators, and what we get will be the following. So we invert this and multiply, these terms cancel. What we get will be 3 times s plus 3 divided by this whole thing, which is, if you open it up, s cubed plus, what do we have? S squared here, 3s squared, 4s squared, plus, how many s? 5s, yes. And you have a 6 here, another 6 there, so you have a 12. So this is the closed loop transfer function. The original system was of order 2. By the way, I didn't talk about the order of a system, right? Order of a system is the order of the denominator polynomial. Okay? So the original system was of second order, G, but the T system, the closed loop system, is of third order, as you see. And poles, zeros, the original system had no zeros. Now it has a 0 at s equals minus 3. It has 3 poles, whereas the original system had 2 poles, etc. And you can make shift the poles of the system to better or worse places. You can make a unstable system stable or a stable system unstable by using feedback. Okay. So, so much for the block diagrams. You can analyze the block diagrams, and most of the time we will be using a feedback connection like this one. It is quite useful. It is possible to have 2 feedback loops inside each other. Let me give you one more example. Let's say let me just check something. Maybe if I use this one. Maybe this will give me a better. So there is a feedback loop here. There will be. We will have another feedback loop. This is the inner feedback loop, as you see. And let me do something. I forgot that. I can put another block here. Let's call it H2. Let's call this one H1. This is Y. This is minus, this is plus. And as you see here, this is another block diagram where you have two feedback loops. This is called the minor feedback loop. Minor loop. And this is kind of the major loop, if you like. Major loop. And in both cases, you have negative feedback. Okay? Negative and negative here. Which means that we are subtracting this signal from the R. We are adding up this signal and subtracting this one. So if you analyze this, the minor loop, for example, we can find that, let's call this thing M, so that the M is the input to this system. Y over M is going to be, we have analyzed this before, so it is G2, G3 divided by 1 plus G2, G3, H2. Okay. So if you look at it, now we have reduced this minor loop. What we are left with is the following. R. I'm just going to draw the major loop here. We have G1. Now this multiplies this thing, G2, G3, 1 plus G2, H2.
Excuse me, John.
Yes.
Why is it Y over M, the minor loop?
Just a second.
Shouldn't it be like Y over R?
No, the minor loop is this one. Let me just put it in a circle. This one.
Oh, okay, sorry, thanks.
Okay. So I have reduced that and put it inside this box. Now we have another feedback loop, which we can reduce again. So it is the closed loop transfer function, which we will call S, which is Y of S over R of S, will be the following. The forward loop, which is G1, G2, G3, they multiply, divided by 1 plus G2, G3, H2, divided by 1 plus this thing multiplied by H1. G1, G2, G3, 1 plus H2 times H1 So if you substitute in the details, what you are going to get will be you will equate the numerator, denominators, etc. And eventually you will get G1, G2, G3, 1 plus G2, G3, H2 plus G1, G2, G3, H1. This will be the total closed-loop transfer function. I'm going to continue with the dynamic response that is of different kinds of systems, first order, second order systems, and so on. But let me give you a very basic introduction to this. Let's say that we have a first order. Dynamic response, first of all, is very much influenced by the poles and zeros, especially the poles of the system. Simple example is G of S is, let's say, 1 over S plus some A. A very, trivial example. This is a first order system. Okay. Now, the impulse response of this system is, as you know, is the inverse of 1 over S plus A, and that will be e to the minus AT. Or is it? Yes, it's e to the minus AT. For t greater than 0. So, if you have, if A is greater than 0, we have e to the minus AT stays a stable response. Whereas if A is less than 0, we have an unstable response. Remember that the pole of this system, pole P, is equal to minus A. So if the pole is negative, the system is stable. If the pole is positive, the system is unstable. Similarly, you might have different kinds of poles. For example, you might have complex conjugate poles. In which you have, let's say, something like 1 over S squared plus S plus 1 is, let's say, is the G of S. Where the poles are minus 0.5 plus minus J. Or we might have, different poles like these. We can represent these poles on the complex plane like this one, the complex plane is the following plane, where you have the imaginary axis is the y-axis, and the real axis is the x-axis. Okay. For example, I gave you two examples. For example, if A is here, we can put a minus A pole here. By the way, we show that this cross sign means the poles, and usually the small poles, and this small circle means the, although it doesn't look like a circle, zeros of a system. Okay. You might have complex conjugate poles like this one. As I have said, for example, this might be minus 0.5 is here, and this will be 3/2. The other one, the other example. The poles locations and the zero locations, if there are any zeros or poles, represent, well, show how the system responds in general. You might have other poles like these at some other places, or some zeros somewhere. The zeros are shown by these kind of things. Okay. The main thing is that there is a dividing line, which is this imaginary axis. And if you have any poles on this side, you have an unstable system. Whereas if the poles are here, you have a stable system. Okay? So the complex plane is the dividing line. The imaginary axis on the complex plane is the dividing line between stable and unstable responses. For example, if you have a pole here, I'm just showing this. If you have a pole here, the response you will get on the time response will be an exponential growth. Whereas if you have a pole here, the response of that pole is going to be an exponential decay. And if you have complex poles, the response would be an oscillation like this one. Okay, stable oscillations. Whereas if you have poles here, for example, you will have unstable oscillations. Okay. So the complex plane represents you can represent the poles and zeros on the complex planes. The important thing is poles affect, let's say, stability. Zeros don't affect stability, if you like, but they affect the transient response. Zeros change the transient response of a system. One last note, then I will stop. The order of a system, let me write this down. G of S, as we know, is N of S over D of S, numerator over the denominator polynomial. You have, S to the N plus A1, S to the N minus 1, etc. And then V1 S to the M, etc. N is the order of the system. N is the order of D of S is the order of the system. For example, you might have a first order system, second order system, third order system, etc. We will be looking at first and second order systems more in detail, but I guess it's a good time to stop here. We will start for first and second order systems the next time. Start with them. Okay. So, I'll be stopping recording.